welcome back. We continue discussing this flapping blade model dynamics. And so, just to recap with that, we have looked at the simplified system with no offset and considering different combination like with rotation, without rotation, with spin, without spin, and both having spin and rotation with no offset. Now we'll extend that same analysis for with the offset case. So now what we'll do again, we'll go case by case. So first we'll take rotation, spring, and offset. So in general, the a real blade does not behave as if it had a hinge spring right axis of rotation. So what that means in general, what it is that omega square would never be equals to omega nr square plus omega square, which we have found earlier. Since the real blade doesn't behave as if it had a hinge spring right at the axis of rotation. So now to correctly model blade motion and the blade dynamics, which are represented by both omega r and omega nr, we need to properly describe. So the properly describe the expression for that. So how we can achieve the same by including the non-dimensional hinge offset. Okay, so that's how we are going to find that out. Okay, that is E. So this E can be thought of as the fractional distance from the axis of rotation to the location of the blade hinge. So now what we can do that we can actually estimate all the constant of the hinge spring model once we know the natural frequencies of rotating and non-rotating real blade. So that means knowing omega r and omega nr of real blades allows to estimate the constants in hinge spring model. So once we know that, we can actually estimate all this. So all this constant in these things. And the offset can be defined as 2 into -1 divided by 3 plus. So this is as per the literature given by Eggleston and Stoddard in their book. So where Z is given as omega r square minus omega n square by omega square. Okay. So we have this offset, which is the fractional distance from the axis of rotation. And this is what we have shown in the picture here. If you remember this, that is what we have taken, that E introduced here, which is the offset. So, okay. So now, in addition to the offset, or this can be accounted by adjusting the moment of inertia. So that means this offset can be adjusted by accounting in moment of inertia. So the mass moment of inertia now will have IB equals to mb r square by 3 1 minus e whole cube. So this is mass moment of inertia of the hinge blade. Okay. So this is where you take into account then my flapping spring constant, that is K of beta, can be estimated at into IB. So here one has to be careful that the rotating and non-rotating natural frequency may be calculated by other method or from measurmental data, whatever is available. So what it shows that the flapping characteristics uh, of the blade are modeled by uniform blade with an offset hinge, uniform blade with an offset hinge and spring that has 1 degrees of freedom, and that responds in the same manner to forces as the first vibration mode of the real blade. So essentially, this responds in the same manner to forces as the first vibration mode of the real blade. Okay. So similar constants can be obtained for lead lag motion of a real blade. Torsion requires a stiffness constant, not require any offset hinge model. Okay. So with all these constant, the blade model allows for 3 degrees of freedom. So all of these allows 3 degrees of freedom, which are flapping, lead lag, and torsion. So what we now, once we introduce that offset characteristics in the mass moment of inertia, then the spring constant can be obtained, and then one can find out these flapping characteristics, but obviously which is modeled with an uniform blade with an uniform offset and hinge. So that would have 1 degrees of freedom, and that responds to in the same fashion to the forces as the first vibration mode of the real blade. So that means how the real blade would respond to the vibrational mode. This would behave in the same fashion, so that you obtain the similar kind of characteristics. Then also, if you include the lead lag motion of the real blade, then we get some constants. Then torsional stiffness can be included. So with all these, all the 3 degrees of freedom would be included, which includes flapping, lead lag motion, torsion, and then we can write the complete equation of the full flapping blade model with free motion. So that kind of writes that. So we write equation of motion, full flapping blade model, which is free motion. Okay. So here, including gravity and an offset. So the free motion looks like beta double dot omega square 1 plus epsilon g cos psi plus a beta by ib complete system, where g is the gravity term, which is kind of equals to mb rg by ib. Rg is the radial distance to the center of mass. Epsilon is the offset term, which is given as 3e divided by 2 into 1 minus e. Psi is the azimuth angle. Okay. So this is what the complete equation looks like. That includes the free motion of the full flapping blade model. That means there is no extra forcing term. So that would be our next set of complications to incorporate. This is where you have all the term. Now we try to kind of derive this, how we obtain that. Okay. Now we'll go to the derivation of this, derivation of free motion. So let us define a system here first. Okay. We have this. So this is GDM. This is psi. This side R cos beta omega square dm. This term is G cos psi dm. So this is kind of a flapping blade viewed from downwind direction. Here G is the gravitational force, M would be mass, R is radial distance from axis of rotation, beta is flapping angle, omega is rotational speed, azimuth angle. Okay. So here, so this is, so what we get is that the blade is turned out of the plane of rotation toward the viewer by the flapping angle beta. So, and the azimuthal angle is psi. So, if you remember that, so this flapping angle beta is the blade is turned out of the plane towards the viewer, and the zero azimuth angle corresponds to the blade tip pointing downwards. This is what, if you remember earlier diagram when we were talking about the aerodynamic analysis. An azimuthal angle, or it increases along the direction of rotation. Okay. And the flapping angle is positive in the downwind direction. Okay. Now, what we do in our further discussion, that it would inputs may vary as the sine or the cosine of the azimuth angle. So we will commonly use that as a cyclics. So essentially, cyclics, the term that we will use, that is cyclics of cosine or sine cyclics. Okay. So essentially, these are the cyclic or cyclical inputs of the turbine response. In this particular figure here, you see two forces act along the axis of the blade on the element of the blade with mass dm. So this is what two forces. The gravity component due to the weight of the blade depends on azimuth. Now the equation of motion of a flapping blade without an offset uh, which is subject to restoring forces due to rotation, restoring forces due to rotation, which is essentially centrifugal force, gravity, the hinge spring, and inertial forces due to acceleration. That is what we will develop here. Okay. So essentially now first we'll start with the modified equation. So the modified equation of motion for a blade with an offset is then first discussed, and then the full equation would be developed, which will include the offset. Now we'll draw another picture here where we'll so one is r square beta omega square dm, r beta double dot dm. The other force is g cos psi dm. This is beta. This is r omega. Here you have k beta. Okay. This is flapping blade viewed from above. Okay. Now, so this is essentially looking down the y double prime axis. So here we also include this flapping spin constant and flapping acceleration. So this includes k beta and flapping acceleration. Okay. So both of them are included. So now we can summarize or all these forces. So first you have centrifugal force. So it serves to bring the flapping blade back into the plane of rotation. So this magnitude depends on the square of the speed of rotation, and it is also independent of blade azimuth. Centrifugal force always acts on the center of mass of the blade, and which is perpendicular to the rotor's axis of rotation. So now from this particular figure here, what we have drawn, we can write that Fc is R cos beta omega square dm. Okay. And the moment about the flapping hinge axis, so the moment about the flapping hinge axis, which is mc, due to Fc, we get mc equals to R sine beta R cos beta omega square dm. Okay, so we get both centrifugal force and the moment. So what it does, so if you see this particular picture here, which is looking down to that y double prime axis, which includes both the spring constant k beta and the flapping acceleration. And then we summarize all these different forces. So to start with, we have included this centrifugal force, which is going to bring back the flapping blade into the plane of rotation. So we have both flapping force and the centrifugal force and the moment. So the next one we'll consider gravitational force. So acts downward on the center of the center of mass of the blade. So when the blade is up, gravity tends to increase the flapping angle, and when down, it tends to decrease it. So this is independent of rotational speed. So there is no dependency on the rotational speed. So this is what we get. So essentially, now we have this, we want to derive this free motion. So we have this blade that has been kind of given that, and then we are considering looking down through the y double prime axis and considering each of these forces. Start with centrifugal force, then we are talking about gravitational force. So we'll stop here and continue this discussion in the next session.